Okay, that's good.
Here.
Let's see. Anyway, yeah, I messed up on the thing about the Leonard Jones. So the potential, so that energy is actually negative. Like it's 3. So that's the depth of the well. It works out. And then one of the groups did the calculation, and the other groups kind of said that. The undergrads I didn't look yet. So the undergrads, you guys, so there's only one here, right? So the other 2 guys, oh, 2. Okay, so you turn, anyway, are you guys okay with the homework setup, or it's kind of like something happened, but I don't know.
The homework?
Yeah, I mean, I got 2 sets, and then I don't know if you're communicating with each other. But,
I don't know really.
okay, all right, so everything's okay. All right, let me know if it isn't, like, as far as the group homework thing, you know. So if it isn't, we can do whatever you want. I was thinking it might be better in retrospect to like mix the undergrads with the grads, you know, because you might learn more that way. But on the other hand, it's a different course, and it's like a different grade, kind of like an undergrad grade and a grad grade. So anyway, who knows? Doesn't make much difference.
It's a bit late.
Yeah, it's kind of late. Like, yeah, no, anyway, there's some problem came up this week, so that's why I mentioned it. But anyway, if you guys want me to do anything, just let me know and I'll do it, put it that way. So anyway, the potential here is like the depth of the well, so it's a negative energy, you know, it's positive. So that means a -3 means that the polymer nanoparticle are more attracted to each other than, in other words, they have a deeper well than the polymer nanoparticle. So that makes everything kind of consistent with what he said. So I was kind of looking at it the wrong way.
It makes me wonder why they chose that though.
Yeah, it's kind of weird.
Why do they have a stronger interaction than,
Because if they didn't, the whole system would phase separate.
I
So it
guess?
has to be a fundamental premise of your model, or else it doesn't work.
Right,
Yeah, they
yeah,
did everything in dimensionless units, but that's good, except when you have to like actually give numbers for like, okay, the ratios between things.
yeah. Well,
I don't know where they're getting those. It's kind of,
they get, all right, everything's based on the kinetic energy, so they can get the temperature, you know. Like you take the kinetic energy of everything in the system, and then from that you can get the temperature. That's like KT. So then at that point, you connect it to reality. I mean, you can always argue that it's not real. I mean, it isn't, but basically,
but they're not really, it's not a real system in the first place, so. If
right.
you
I
found
mean,
a system that had these parameters, then I guess it's real.
yeah, yeah, the other thing is this thing isn't based on any physics, right? It's just like, I think it's just a guess, right? I mean, it's just like, seems to work okay.
Yeah,
So
I think it's like slightly better than a hard sphere potential, but like,
well, oh no, the 6 comes from van der Waals, I think. The 6, I think, has reality to it.
you know, you might be right, because I think the 12 is just there to make it mathematically easier.
Yeah, the 12 just makes us take a dive here. So maybe that doesn't matter that much. I think the 6 comes from the van der Waal, something about van der Waal interaction ends up being 6, like the volume squared or something. Anyway, the other thing interesting, like Leonard Jones. All right, so the guy's name was Jones. It's a guy, and he married a woman named Leonard. And he hyphenated his name, and it was in like 1905. So it's a long time ago. It's pretty weird. Anyway, that's like probably the first person that did that, I guess. I don't know. So it's pretty weird. So it isn't 2 people, it's just 1 person. Yeah, I know. I always thought it was 2 people, or usually it's 2 people, and it's like that. It's just a hyphenated name. Like, that's from Wikipedia. It's not any insightful thing, but I thought that was kind of interesting. Anyway, see, otherwise everyone seemed to get this. I don't think there's anything else. Any other problems with this, like the pain effect? People went, looked at it seriously, kind of went through it. Seemed okay. I'll probably go back and give you guys some more points for where I messed up the Leonard Jones thing and you guys got it right. So I might go back and just, anyway, you don't really need any points. So it's not like everyone's doing well on there. Then I got the COVID shot, my 4th shot yesterday. So yesterday I was pretty wiped out, so I didn't get much done on the stuff. But I did kind of finish up the Rouse thing. So we can, I mean, the reputation thing, which is just short. There's a lot to the reputation thing. There's a pretty good, like this book by Rubinstein Colby's, I guess, okay. All these books have some defects in them, so like down at the end of this, chapter 9, I think it's definitely chapter 9 because he ends the book with this stuff. So he devotes, like he goes through reptation, entanglement dynamics. Right? So, and then he gives a simple answer to like how reptation works. And then like he goes on for like probably like 30 pages about different manifestations of reptation, like how it, so anyway, a lot of these seem to be topical. In other words, like you pick up a paper, if you know the first part of reptation, you can kind of figure it out. And then like there's a simple idea about reptation, then there's things about tube renewal and polydispersity of chains, and then a couple other features that are at some point like you don't need to know that. The only thing, so this was kind of interesting. Like he's showing you have a star polymer. So this is the standard crossover. You have the linear polymer. So this is G prime. And it reaches a rubbery plateau and then goes up. This is G double prime. And then it goes down and then back up. Right, so that's the crossover, and there's another crossover here. And then he takes a star of the same stuff. This is what the star does. It has a crossover and then kind of a plateau. But then when you reach high frequency, it becomes the same as the linear. You know what I mean? Like, so you just look at the arms of the star at some frequency. As you're getting to smaller and smaller sizes, once you reach the kind of the size of the arms and frequency, then they have the same behavior as a linear. So I mean, so there's nuances like that can go on and on. There's no limit to it. Like he does that for cone polymers, like viscosity enhancers, so H polymers and cone polymers. And this is like the shape of the molecule. H would be the shape of the molecule. And the cone is just like got a lot of arms off it. So these are kind of like, we could pick up a paper and look at each one in particular and spend a quiz or homework on it, but basically there isn't much new. There's new information and kind of interesting things like that, like the things you can like describe the behavior, but it isn't like the fundamental part of it. So even though he spends a lot of time, like his octopus polymer, it's like this is like important to polyethylene because if you have long chain branching, then each of the branches has to relax. You have to wait for that reptation of each branch before the whole molecule can kind of move along. So this model is like popular. People talked about it, but again, like, and then the snake in the woods thing is like another one that people talk about, but I don't think that stuff is that. I'm not sure it's of much value because it gets pretty confusing and it's a lot of math, and it's detailed. So I'm not sure beyond the tube idea that it's really worth looking at it. except in the sense like I can find a paper where they talk about the snake in the woods or something. You can kind of figure out what they're talking about. So anyway, this chapter 9, a lot of the stuff I'm getting is from that. And then I put up also another, should have done that. Put up another book that's like pretty, the last chapter of this book is good. This book by oh, maybe I didn't put it up. Maybe it's my McCosco here. I put it up there. I lost my actually open. I had to. This is an old book, but it seems to be pretty good if you're interested in rheology. Maybe it isn't up there. Anyway, I'll fix that link if it's not working. It's an old book on rheology, but the last chapter is pretty good on reptation and stuff. This McCosco book. McCosco's a guy from Minnesota. Minnesota is like the top chemical engineering school. And it's mostly because it's like half polymer and half chemical engineering. It's kind of weird. So it's also one of the top polymer schools, but mostly for this kind of thing like rheology of polymers. So McCosco is like the father of that stuff there. So a pretty old guy now, but anyway, there's a thing called the Bingham Medal, which is a Society of Rheology gives out. So all the top rheology people get that medal. So McCosco got it. This guy Winter got it too. So I'll talk about Winter later on. One of this thing about gels. Let's see. So anyway, so the Neros. So let me just flip through if there's anything that you take. Through that business. See, I'm not sure. Yeah, we did this, right? That if you get to low frequency, like you have this equation for G star, which comes just from the compliance, complex compliance is the imaginary divided by the viscosity. So the slope at the low end, I mean, the low frequency end would be just the 1 over the viscosity. You take the inverse of that and then do this complex conjugate. You get this equation. So you have the two parts, the real and the imaginary. So this has to do with flow, and this has to do with the modulus. And if you go to low frequency, then this thing becomes less than 1. So you can just say that's 1. Then you just have the square of the frequency, and this is the linear of the frequency. So the whole thing about the square and the linear is just kind of just comes out of this complex conjugate thing. Seems mysterious, but it's just straight from that. So the slope in the flow region for the storage modulus is the square of the frequency. For the loss, it's just the frequency and the slope of the line in a log-log. The slope of the line, it doesn't have to be log-log, it'll still be a line, is the viscosity. So basically the loss modulus is the viscosity, but it's got this time dependence part to it for flow. So, and then it's kind of odd that you see that when you get to the high frequency end, it shows this Rouse behavior, which is a square root. And that comes from, that square root comes from basically, we had this in the last quiz, right? That the relaxation time for mode P goes with 1 over P squared, and it goes with the molecular weight squared. And then if you're at some, so everything, so if you have a list of modes from from 1, where it's a whole chain. So 0 is the translation of the whole chain, and 1 is just the first vibration of the whole chain. And then you can divide the chain up into nodes that'll have like, so the 2 is like where it's a full sine wave, right? So anyway, so if you have larger modes, so their relaxation time is shorter. So if you're at the time of relaxation for the P mode, then every mode less than P, every mode of P higher modes P is already relaxed, because those are all higher frequency. Those are all shorter time. So if you're at time P, everything is shorter time, which is of higher mode, is already relaxed. So you can forget about those. Those don't have any energy on them. And then the modes lower have energy. So you have P modes that are contributing to the energy of the system. Right? The modulus has units of energy per volume. So modulus is energy, basically. So modulus is always going to be proportional to KT, because it's going to be the energy, and it's just a matter of how many, and each KT is for each unit of the stuff, like each piece of the thing you're looking at. So every piece has a KT energy. So you need to know how many pieces have KT. When you have that, you have the modulus. So modulus is going to be KT times how many things, each thing having KT energy. That's the idea. So all these things are going to be like KT times something that ends up being a number, like how many. So how many is, so if you have, let's see. So you have time T, which corresponds to some P, like any time. So you have a relaxation spectrum G of T. So you're going to plot modulus versus time, and it's going to have like a decay to it. So basically, you're talking about any value of T, modes of P smaller than whatever P is, right? So there's going to be, and for those, the number of those segments, so they're going to have N by P monomers of volume B3. B is the monomer size. In other words, the total chain is N, and for P mode, you divide N by P, and that's how many monomers are in that node of the vibration. And each of the monomers has a B3 volume. So you have the volume. If you have the volume fraction putting N, you divide the volume fraction by the volume of the units that are vibrating, you get the number of segments. And that number of segments times KT gives you the modulus. So that basically gives you this time-dependent modulus, shear modulus for the system. And if you work through that, so because P is here, so P goes with square root of time. So P goes, because tau P goes with 1 over P squared, like in that paper. So that means P goes with square root of time, and P is proportional to N. So that means you have this relation for P. If you have GP as this equation from this volume of a unit times the volume fraction, then you can plug in for P here, then you can get, and TP is the actual time, then you can get the square root of time dependence from that. Because you have square root of TP divided by it, and you end up with square root of time for the time dependence of the modulus. And then that just translates into frequency, like this minus 1/2, this becomes 1/2. So you just have the storage modulus goes with 1/2 of the frequency. Like I said, everything is a lot of math, like it's a lot of steps, but basically it's kind of logical. I don't know. So it's like if you want to go into like how a star polymer or something, it's going to be more steps like this. So I'm not sure where you get the things to remember are just like these general rules. It goes with square root of time, square root of frequency, and that's the thing you see like at the high frequency end. You see the square root of frequency, but so why it's occurring here? So we know about the flow part. That's kind of straightforward. The plateau part is because the entanglement, you're only looking at entanglements at that point, that's fixed. basically you get a plateau because the entanglements don't change until you reach the frequency of relaxation within the entanglements. And you see reptation. You see within the tube, you see transport that follows Rouse behavior. It's 1/2. So Rouse is for dilute, but when you have this is for a melt. So with a melt, you see a plateau. Again, there isn't like one law that talks about the whole thing. There isn't a function for the whole curve. It's just parts, like this part, that part, and that part. You explain them separately. You know, there's no like one rule for the whole thing. So anyway, so this 1/2 that you see here is because you have Rouse behavior within the tubes. So that things are behaving as if they're unentangled chains when they're inside the tube. And the entangled chains are just showing, because there's only one size scale, it's just the entanglement molecular weight. So there's only one modulus for the plateau part. So that gives you that. And if you say, you reach the tau 0 is the relaxation time of one monomer. So if you go, so for times bigger than the one monomer, then you also have the relaxation due to the Rouse, and then this is the relaxation due to what? This is the relaxation due to the modes, and everything has to have this exponential term tagged onto it. I guess is what it amounts to. Like this is the mode part. It's like a prefactor. Everything has to have this exponential decay part to it too. So anyway, the curve for the whole Rouse. So the Rouse part is this 1/2 dependence, but it's going to have a point where in time where that 1/2 dependence disappears, where you reach the relaxation, the shortest relaxation time for the entire Rouse unit. And then you're out of Rouse at that point. So that's mode 1, and then you have an exponential decay at that point. Right, so this when you're at T's much bigger than tau R, this thing doesn't matter, but then this thing comes into play when you get near TR, then you get exponential decay. So that gives the entire time spectrum by the Rouse model. It's kind of like this thing that comes out of just the dependence of the mode behavior, and then this thing which is like the whole unit. So there's 2 parts to it. So anyway, if you have that, then you can do this integral. So then you can say like G prime, it's a sign dependence of GT, which is that thing. And G double prime is a cosine dependence of that thing. And then basically you can get these 2 equations, which are, so these are the Rouse storage and loss modulus equations. They come from basically take this equation, plug it into the integral to get the loss and storage, the storage and loss, then just do that integral and get these 2 equations. I haven't done that. I didn't really get to do that. So basically, I'm just accepting that this is what the answer is to that integral. It doesn't look like it's that hard of an integral, but I just didn't kind of have time to do it. So if you want, you could do that. But basically, these are accepted. And then you look at these 2 equations within different ranges. So for one thing, you can say that if the frequency times the Rouse time is much less than 1, then this thing is 1. And then that thing is 1, because this is 1. Square root of 1 is 1. And I guess this thing is 2. This thing goes to 1. That thing goes to 1. Something's 2. 2 times 1 is 2, square root of 2. So you end up with a square root of 2 here. Yes, but anyway, the dependence is square frequency, which is G prime for a fluid. Right. So if you're at a really low frequency, then it acts like a fluid. For this, and for this thing, very really low frequency, this becomes square root of 2, and this thing is 1. So basically, it's got just frequency. So it acts like a fluid, both for storage and loss when you get to a low frequency. if you're at high frequency, then you can forget about the ones. So if you're at high frequency, something weird happens. Okay. So if you're at high frequency, let's see, you have squared and then square roots. That becomes frequency, and then the one you can forget about because frequency is high. Right. And then so you have frequency times frequency. Forget about one because this is larger than one. So you get frequency cubed. And square root of that, so 3/2. So 4/2 minus 3/2 gives you a square root of frequency for modulus and this prefactor. Okay. And then if you have this loss modulus, so you have the square of the frequency, and then this is the square root of the square. So that's just the frequency. It's bigger than one. So it's the frequency divided by the frequency squared. So that gives you 1 over the frequency square root. And this is, so you end up with frequency squared for this thing also. So both of them have the same, and they have the same prefactor. So that means that when you get to the high frequency limit of this thing, the two things are the same. It's weird. So this is just fluid. So this is how the dynamic modulus looks for actual Rouse. So for a polymer that's lower than the entanglement molecular weight than against frequency. So this is a real Rouse test of the Rouse. You have flow here. So you have power 2 for the loss and power 1, or power 2 for the storage and power 1 for the loss. And then they just go the same, and the slope is 1/2. That just, the 1/2 just falls out of that equation. Right, so it's kind of weird. Anyway, so that's not the only place where you see this 1/2. So it turns out this 1/2 slope occurs in matching slope of both the storage and loss of 1/2 occurs in like a lot of different systems. So this is a simple thing, and the Rouse thing works for it. But this guy Winter and a guy named Chambon. So Chambon, I think, was like a visiting postdoc or something. Right? And Winter's another big and metal winner for the viscosity rheology society. So in '86, I mean, this is the viscosity of a liquid. So you're going through a solid gel transition where he's taking PDMS, so silicone bathtub sealant, and then you cure it, and it's a sol here, so it's a viscous liquid, and then over here it's a rubber, right? And then you get to what they call the gel point where it forms a solid. And at that point, you have G prime, G double prime versus frequency, log, that's 1/2. Right. So when it gels, it forms a network, it takes this 1/2 frequency dependence. So he's showing like he's picking points as a function of reaction time as he cures the bathtub caulk. It's purified bathtub caulk. So basically his point where the G prime overcomes G double prime is where he says it becomes a solid, and that he calls the place where it percolates. At that point, he gets this 1/2 thing. This kind of gel thing is all over the place, right? I mean, if you're talking about goo, then gelling goo is like one of the main themes. Yeah. So this is kind of an important paper. It's got 3,000 citations, this paper. So that's a lot. I mean, in the biomedical community, there's a lot of, like in medicine, there's a lot of papers that have 3,000, but if in rheology, there's probably only like 2 or 3. You know, I mean, it's not exactly, they aren't beating down the door for this. You know, so I mean, no one's going to live or die if you can tell about the gel point. But basically, this is a pretty high citation. So he's a nice guy too, Winter. You know, so anyway, so I'm biased, but anyway, so he came up with this thing like, well, it's going to be a power law frequency. Then he did something kind of interesting. So finding that alone was like probably why he won the Bingham medal, you know. But then he figured out like Kramer's Kronig that we talked about, that he thought had no use, right? It probably, arguably, has no use. So if you plug in his function if you plug in just this arbitrary power law of frequency into that function for the Kramer's-Kronig, which this rules the world. In other words, everything has to be like that the loss comes from the storage and the storage comes from the loss, because there's only two parameters that define all rheology, right, for any material. So anyway, he plugs in his function, then he reduces it to get just in terms of this integral, this term n in it. And he finds out that n for this solution of 1 can only have value of 1/2. If it's negative, it's not a physical material. So basically, just by going back to the Kramer's-Kronig, which is kind of like the 10 commandments or something of rheology, he can find out that this n has to be 1/2, which is the same answer that you got from the Rouse thing. So it kind of says, if you have a power law dependence of these two things, they have to follow a 1/2 power law with each other, if the world is fair. So anyway, that's kind of this business. I put that winter paper up on the webpage. It's in the book section at the end. It's from a long time ago, but anyway, it's like here. So look at it if you want. You can see like it's old because it's not digitally typeset, right? Well, no, it's typeset, but this is a photograph of a. They went through printing, went through a series of things. The original is you typed it. I mean, the original they had to set the type. Anyway, this is somewhere intermediate between those. You can see it's like if you zoom in, pretty low resolution on it. Also, the graphics are like some of them. Get to really old papers, the graphics are hand drawn. These are almost hand drawn. These are printed, like these graphics are made on a PDP computer, some kind of old, like it was a computer that took up a whole room. I mean, so these graphics are really old. You can kind of tell where they came from anyway. So anyway, but that paper is still important. Like if you go to the, like people are citing this paper all over the place. But yeah, 3,000 citations, but just mentioning it, like they just say, oh, this winter shambolic behavior, it means like it's goo. So it's acting like this gel. The weird thing is though, so you'd think that the entanglement would be like that, in other words, so there's something different between a gel, a percolating gel, and an entangled melt. Because the entangled melt, the plateau modulus is just a constant value. So it's because the entangled melt has this fixed size to it, and this gel thing has kind of all different sizes. Right? So there's fundamentally, so they don't really get into the nuances of things in these rheology books either. Like they only say, also they contradict, like if you actually calculate the equations, they don't come out exactly right every time, but nonetheless, it's kind of an interesting area to look at. So it's that business. Then what else is going on here? So is that. So this is the same as Rouse behavior, this gel behavior. It's going to have that same square root dependence. And I mean, Winter goes through that this is infinite. Later on, in his papers later on, they talk about more about like what a network is, things like that in terms of rheology. But this paper just like observes it, does this Kramer's-Kronig thing. So what else is going on here? Let's see. We already did that, so kind of beaten that to death. Oh, then the reptation thing. So this is just all right. So the idea is, I forget what this is. I think this is from the McCosco book in the last chapter, which is by a guy named Matt Terrell, who also has won the Bingham Medal. So Matt Terrell's, there were two Terrell brothers. They still are around. The one is Dave Terrell, who's a chemist, and Matt Terrell's a rheologist. They're both really nice people. So Matt Terrell's Minnesota, right? Part of this rheology thing in Minnesota. That's why partly why he's in McCosco's book, because McCosco's like Minnesota. But he's more of a fluffy, like French kind of theory guy, like dynamic light scattering and stuff like that, rather than McCosco's a real rheologist, like an industrial rheologist, like Polymer industry. So anyway, the last chapter, Matt Terrell writes, and he goes through reptation from whatever year that book was, like in the 1990s, I think. So, but anyway, this is the idea, like you have this mess, like you have no idea how to figure out what's going on. So you say like there's this confined region that's defined by the entanglements that the chain will have to be kind of moved through if it wants to move, because it can't move the other chains. In fact, it can, but basically, and if you're talking about moving this chain, the walls that it's moving through are made of the same thing. So everything is actually relaxing, but the simplest form for a patient just assume those are fixed, right? And it's moving through, or almost like a polymer chain moving through a network, like a snake in the trees. That's the Jens wrote that it was a snake in the trees. So then you simplify that even more and just say it's a tube, right? It's got a tube diameter, then it's got these subunits that you just say are some kind of blob, like they're a reptation blob. So they're like Rouse units. They're basically Rouse units, they're a fixed size. They have to do with the entanglement density. So the size of this is a square root of the molecular weight, the entanglement molecular weight. So this size is going to be just entanglement molecular weight square root. And then, so in the Rouse, that's not fixed, but here that's a fixed size, right? So they say in this thing like kind of moves in a one-dimensional. So if you have one-dimensional diffusion, the difference is 2. So you have the average root mean square distance it travels, which you can go forward or backward evenly, is going to be 2 in 1 dimension and 6 in 3 dimension. So this prefactor changes. That's the only thing that changes. So basically, it's just a diffusive equation. You can plug in the Rouse function for the diffusion coefficient, which is that it's the inverse of the molecular weight, which we got, and you probably have forgotten. So you plug that in, and you can get this time, the time that it takes to go the length of one of these blobs. So the length of the blob goes with n, so it's n squared, and then divide by this thing, which is n-1, gives you the reptation time. The time for this thing to move down the tube is n cubed, goes with n cubed. Right, so that's what we saw in the plot. I don't know if I have that plot here. Yeah, so here you have Rouse, viscosity goes with n to the 1. And then here, viscosity goes with the n to the 3.4, which is close to 3. And to get to 3.4 involves a lot of math, and still isn't actually reached. So anyway, so we had Rouse, but the relaxation time for Rouse goes with n squared divided by p squared from that paper. Right. Then here we have reptation, goes with n to the 3. Then the diffusion for Rouse, if you take that reptation scaling and then take r squared goes with n for a Gaussian chain, and you get reptation. Diffusion goes with n-2, and for Rouse goes with n-1. And then from the end of the 3, if you say that you have, you say that the reptation time is going to behave like it's got a normal viscosity divided by modulus, and in this region, the modulus is a plateau modulus, so it's fixed because it's got the entanglement molecular weight. So it's just the fixed plateau modulus in the reptation region. Then this tau reptation, which has power 3, is the same as the viscosity. So viscosity is going to follow power 3. And it's going to have the entanglement molecular weight KT as a prefactor. So it's basically you can predict kind of the 3.4 just from saying the things in a tube. And it's following Rouse dynamics, 1D Rouse dynamics. That's it. That's all I want to say about reptation, because the more of it is going to just get more. This is already confusing enough, So I'll find some paper, but basically, I think those are the general rules. And they kind of back of the envelope figure out where they came from. but then again, like there's a lot more to it. Like you could go on and on about reptation and get kind of nowhere. And I don't think it's that helpful to do it. So that's kind of that business. Then there's this other thing that I haven't actually finished doing, but so when you like when you push a polymer through a die and then it swells, they call it die swell. So if you push water through, it just goes straight, it doesn't swell sideways, polymer swells sideways. And so comes from this normal stress coefficient. So if you have, so the shear, you put in a shear stress and a shear strain, that's the deck of cards flow, then you get the viscosities and proportionality between those. So you strain it, you push the top card, get a velocity gradient, that's the viscosity. Here, so this is just a constitutive, the definition of it, right? So here you have the stress difference between downstream, like a tensile stress and the normal to the tensile stress. So you're stretching the fluid, and then the normal stress shows up. So there's a coefficient that relates those. This goes with the square of the, instead of going with the strain, it goes with the square of the strain. It's like the strain squared, and then this normal stress coefficient, which is the same as the viscosity, so it's just constitutive describing how much, the bigger this is, the more die swell you have. And there's two of them because there's Z's downstream here, so X and Y. Normally you'd expect those to have the same value, but they don't for polymers. So there's a reason that they don't have the same value. Anyway, so things are happening. So the way I don't have slides for this, but basically the model that they've used, I mean, you could say like the thing stretches out and then it wants to spring back, so it pushes out. That's kind of a simple way to look at it. But in terms of a shear, so this is a shear flow and not like a tensile flow. So the idea is they've taken a rubber, and then if you twist a rubber, so if you twist a rubber, it kind of contracts and then it pushes up. So that's the model that they use to talk about this. So they'll take like a network. They'll say that the polymer fluid is a network and you twist it and it's going to make this normal force come out that pushes out. And from that, you can calculate kind of what the origin of this is. I'm actually reading out the notes for that yet, though. So there's that thing. That's one part of this. And there's also this, there's actually several of these things. So that's the normal stress coefficient. Then there's also, if you flow it, so if you like pour molasses out of a bottle and then you stop, it'll like recovers back, like it'll flow back in. Like, or if you have a flowing stream, you snip it, it like bounces back. So it's got elasticity. So they call that the recoverable shear strain. Right. So there's also this shear strain that if you stop the flow, it flows backwards. Right. And that changes with the rate of strain also, and it's got this kind of plateau behavior. So it's basically this Newtonian region for the viscosity corresponds to kind of a Newtonian behavior for the first normal stress difference. And then second normal stress difference has the same behavior, just got a different value. And then this recoverable strain is linear. It's linear in rate of strain within the Newtonian region. And then it plateaus out when you get into this shear thinning region. Right. So both the normal stress kind of diminishes and the viscosity drops. At the same time, this recoverable strain plateaus out. So these things kind of tell you something about what's going on with the fluid. And when you get to this point, like the viscoelastic relaxation time, and then all of a sudden you're going too fast with the shear rate for it to recover, and then you're starting to see these weird behaviors show up. So So what else? That's about it, I guess. I don't know. I haven't kind of gotten further on these notes. The old notes, I don't think are good for this stuff. Let's see. What notes are here, but I think these don't have much more. Stuff we went through. Yeah. That's enough stuff. Anyway, any questions or anything? That's probably enough for today. I mean, those pictures of reptation. I mean, these are just the same thing like the tube model. So simulations. So anyway, so yeah, next time I'll probably go through more about the normal stress difference and there's a couple of the things on rheology I want to go through. So hopefully I'll have some papers for tomorrow, for Friday. Right.